Hi guys, I'm going to talk today about neural audio compression and why we need it, and we will cover a couple of recent papers, how people actually make audio codecs using neural networks. I'll talk a little bit about VALL-E because VALL-E actually uses results from this paper, and not only results. It uses actually code and pre-trained model from this paper in Codec, and I'll touch this paper SoundStream because actually in Codec is a slight development or incremental improvement over SoundStream, as it seems for me. I may be wrong, but it seems like this. And actually SoundStream, what they've done, they improved this paper where people used vector quantized variational encoder for low bitrate speech coding. All links are here, and presentation will be linked in the video below. More precisely, we'll talk about these two papers, Encodec and SoundStream. So first of all, let's talk about audio codecs. Just a couple of words, why we need them, what it is, and how people use them. Audio codecs, it's some procedure to compress our audio signal so we can transmit it using digital transmission tools, let's say 5G, 4G, whatever, using just internet tools, transmit it to some another device. Or for example, it can be used for radio transmission. For example, you use walkie-talkie, and actually your signal, your speech can be compressed there, so it would require less demand for bandwidth. Sorry for my pronunciation. To transmit the data. Yeah, basically it's about transmitting the data, compressing and transmitting the data. Once again, about codecs, we have, let's say, two devices. We compress our audio on one device. We use low bandwidth to transmit it, and then we decode our signal and restore it as it is. Basically, that's it. That's the main idea. And the more we can compress our audio signal, the better, and the higher quality of recovered signal is also better. That's it. Let's talk about VALL-E a little bit. Actually, I covered VALL-E in the previous video. Link will be below as well. So why I talk about VALL-E? VALL-E said that this neural codecs actually contain some good semantic information, and they used representations produced by neural codecs to create zero-shot language generation, speech generation model. That's it. What VALL-E does, they use they encode audio signal using actually audio codec. Like neural audio codec, which actually contains some semantic information, and in representation in this space of neural codec of quantized vectors, they create new signal using language model. Basically, we have this language model. Then they use the same codec to decode this signal into speech. That's it. That's it about VALL-E in plain words. SoundStream. This kind of interesting paper. What they do here and how they do it. We have signal. Let's say 24 kilohertz, and we compress it using strided convolutions. We slowly compress it using strided convolutions, and we get 75 hertz. That's it. So we get kind of 320 times reduction with the strided convolutions, which is a lot, but it's not the main point. We can do such things with raw audio signal, and then we can work with it. Later on, we use something called RVQ. It stands for Residual Vector Quantization. We get our quantized vectors here. I'll talk about it more slightly later. And then we have our quantized vectors also with the same 75 hertz. And we decode it. What it means? What does it mean? 75 hertz. It means for 1 second of audio, we have 75 time steps. And here, for 1 second of audio, we have 24,000 steps. That's it. That's what Hertz means. And we kind of squish our audio signal in to have a smaller number of audio steps, but we still need to preserve information, pass this information to our decoder, so our decoder can decode our signal. It kind of resembles a lot autoencoder, variational and autoencoder and such models, but there are some interesting details. So how do we save on transmission? How do we actually compress our audio? We use this residual vector quantization part. And this residual quantization, residual vector quantization part, it quantizes our signal into a code book. So it uses some code book, some number of vectors similar to vector quantized variational encoder. And instead of using this specific code book, we use only indices. I'll cover this part as well, just in a little bit. And by using only indices for this indices from our book code, we can compactly compress our data and transmit it quite efficiently using low resource devices with low bandwidth and with low with bad internet connection and so on and so on. So key component of this structure is here. It's residual vector quantization. And as promised, I'll talk about this residual vector quantization in a bit. And this residual vector quantization is actually connected with how we compress or quantize our data. This is a key component of this architecture. So guys from Encodec. As you see, took the same architecture almost. They kind of didn't change much. You can try to find 10 differences. You can try to look into both papers and try to find differences. It's quite funny. So there are not so many differences. Architecture-wise, authors added RNN. They added transformers for entropy coding. So entropy coding, what it does, it kind of helps to produce better quantized vectors, better centroids to achieve. So in other words, it helps to achieve better compression rates. Again, I'll talk about vector quantization just in a bit. And yeah, it's the same component. Vector quantization here, vector quantization here. It's the same structure, the same idea, and actually, in Codec they used exactly the same solution as in the previous paper, except optionally, that it's important, they added this transformers for entropy coding. In streaming version, which means it can be used in production, it can be used in real time. They didn't use these transformers as far as I know, because it's faster. But with transformers, we can get higher compression rates. I'll explain what it means to have higher compression rates just in a bit. So again, about the game, find 10 differences. Modified architecture, a slightly modified architecture. For example, they Encodec added RNN into the architecture, entropy encoding using transformers, different training procedure. They come up with such thing as a loss balancer, because while training these architectures, we have actually quite many losses. If you see here, we have one loss, second loss, third loss, and how many? 5 losses actually, because we use here something similar to GAN structure, generator and discriminator. We need one more loss to train our quantized representations, and so on and so on. So there are quite many losses, and each loss has its own scalar value in front of it. And what they did with this loss balancer, they actually say, okay, we will dynamically modify these scalar values in front of each loss based on some heuristic. That's it, and other minor differences. Anyway, if you compare quality of SoundStream and Encodec using the same bandwidth, you see that Encodec is better, is noticeably better than SoundStream. But it's not like super different if you compare with Opus or EVS. Opus or EVS, these are standard codecs. And actually, Opus and EVS, these are codecs which are used, let's say, in Zoom, Google Meetup, YouTube, and so on and so on. These are quite popular standard solutions. And you can see that SoundStream and Encodec both work better, even with lower bandwidth. Basically require lower they require lower capacity to transmit the data. Okay, so about what about RBQ? I kind of promised you to talk about these things several times, and I'm going to do it right now. A short recap on vector quantization and vector quantized variational autoencoder. If you're familiar with this paper, it's going to be quite easy for you to understand what is happening here. If you're not familiar, I'll explain quickly. So imagine autoencoder, or let's say variational autoencoder. It compresses our data, but instead of compressing our data into some, let's say, random vector or some vector, it will. And so encoder, it produces some vector from this area, let's say, but we take closest centroid. We take some closest centroid, and instead of passing this vector, this vector, this vector. Yeah, here is these are 2D vectors. In reality, this can be high dimensional vectors. ADA stands. ADA is the same. And yeah, instead of passing this or this or this or this vector, we pass one centroid further to our decoder. Each time it happens this way. So basically, we compress our signal or our image into some vector, and instead of passing, let's say, this vector or this vector, we pass it to some centroid. Number of these centroids is limited, and number of the centroids, or basically these centroids, are called book code or code book, I don't know, whatever. Yeah, and our approach is to learn this centroids, vector of these centroids. That's we call quantization. And right now we connect it with data transmission idea. So once we don't use this big variety of real valued vectors, and we use some fixed vectors to represent our data, instead of transmitting vectors themselves, we can transmit only indices of these centroids. Here n is number of centroids as sequence length, and basically we can kind of calculate how many bits do we need to transmit our data based on number of centroids and sequence length. Yeah, that's it. Because we are not transmitting actual high dimensional vectors, we are transmitting only centroids, and we save a lot of memory, and it's a huge compression to transmit this signal. That's it. I hope this idea is clear. If it's not clear, ask in comments. So what we do next? Let's kind of calculate how many centroids do we need to compress audio with 6K bitrate. What it means 6K bitrate? For example, we can transmit. For example, we have some device which can transmit data limited by only 6K bits. So bitrate, it's a number of bits. That's it, number of bits per second. And we have some limited device which is able to transmit data using 6K bits per second. We can use different number here. We can use 3000s, we can use 5, we can use 24. It's just for example. And basically, this is our compression rate. This is how much we want to compress our data to which bandwidth or to which capacity we want to adjust it. That's it. That's a number of which comes from some device or limitations which come from some device or internet connection and so on and so on. Basically, that's it. So we have our signal with 24,000 Hz, and we slowly reduce it. And it's important that we reduce our signal along time axis, right? and we get 75 Hz here. For example, we want to transmit, we have this compression rate or bit rate which equals 6K, and we have 75 Hz, right? It means we need 80 bits for each time frame. If we need 80 bits for each time frame to transmit all the variety of this data, we need a code book 20 in power of 80, right? That's how many centroids do we need. That's a lot. That's a lot of centroids to transmit our data with this bitrate. And it's not kind of feasible. In reality, people would use much lower number of centroids to approximate this value, but we can do a slightly different thing here. So let's talk about residual quantization. For example, we have a sinusoid here, and we quantize our sinusoid. Exactly the same idea is represented here. I'll talk about it as well. So we have our sinusoid here. Actually, our sinusoid here, here it's going to be, here it's going to be residual. First step, y equals residual. And we have our sinusoid. What we do next, we quantize our residual. We quantize it. And here I kind of plotted this quantized residual, first part. So it's very coarse quantization. It's binary quantization here, but whatever. We have this quantization of our signal. It's here. And then what we do, we subtract our quantized signal, this one, from our original signal. So you see, residual is y, we subtracted from y, and we have some residual left. What we do next, we take this difference, a difference from this signal and this signal, and quantize it again. We get this thing. And we repeat it many times. That's it. So we can reverse this procedure, and here I used 7 components. I didn't plot all of the components here. They wouldn't fit, but yeah, 7 components. And if we sum all of these components back, we kind of can approximate our signal. This is the main idea behind residual quantization. That's it. This one, it's not vector quantization. This thing here is scale quantization in one of its forms. But yeah, the idea stands the same, because instead of using this scale quantization, this quantization operation can be vector quantization or whatever. That's what we do here. And that's what we do with vector quantization, and that's how we get our vector residual quantization. So let's look at this thing right now. We can have right now many quantizers, many vector quantizers. Let's say we have 8 vector quantizers. We have exactly the same setup as before. We have 6K bitrate, we have 24K hertz, and embedding after compression 75 hertz, right? So we computed previously that we would need 80 bits for each time frame, but right now we have 8 quantizers. And having 8 quantizers for one quantizer, we would require only 2 power 8 centroids, which is 1024. And right now, once we have 8 quantizers, right, we need only 8 multiplied by 1024 centroids in total. That's much smaller number compared to 2 in power 80. It's much smaller. And what we have else, we have kind of some flexibility to change quality and computational efficiency of our model, because we can increase or decrease number of centroids, we can increase or decrease number of quantizers, and we have more tools, we have more values to play with to obtain the more optimal solution for quantization. So of course, papers authors, they've done it, and these are numbers they've got. We can look at it, and they try different number of quantizers. So different numbers of quantizers. What that means? It means we have different numbers of these decompositions here, and we can have up to 80 decompositions. But with up to 80 decompositions, we may have code book size equals only 2, which quite interesting, right? It's really interesting. And here we have different trade-offs between latency and memory. Two code books, they do not require kind of a lot of memory. It's super compact, but computing all of these residuals and reverting this computation would require some time, and vice versa. We can have a huge code book, not really huge, but significantly bigger, and a smaller number of quantizers. So we would require more memory to keep all of these code books in memory, right? But also it requires less computations. This option will be better in terms of if we require high latency solution. And let's compare our solutions. So we can see, we also compare for MP3. It's common format for compressing audio, but we also have different formats like Opus here. And we can see that, entropy coded, if you use entropy coded or don't use entropy coded, this is a part with transformers, which I talked about previously, which requires higher latency because obviously we have more computation. And we see compression rates achieved by Encodec, and it's 256. Let's say here we compare it with Opus, and we see that quality is significantly higher, right? That's significantly higher. That's a lot. But for lower compression rates, let's say 64 and 64 here, it's different, but it's not that different. One of the questions which my colleagues have to this paper is that why did authors use Moshra and this Moshra score? Moshra score is a kind of etalon metric for using for comparing different codecs. And yeah, it's a standard for comparing different codecs. That's fine. But when we look into, let's say, speech generation papers or other papers, they evaluate quality quite often using median opinion score and quite many different metrics. And Mushra score is not always perceptually correct, and therefore there is a question: why didn't authors use a mean opinion score or something else to evaluate the results? This is a question for this paper. This question for the results. So just take it with a grain of salt. We can see that according to Mushra, this solution is much better, but it would be nice to see different metrics as well. That's my point. And kind of the same results. We can see again results using entropy coding here, and they're slightly higher, and results without entropy coding, just using Encodec here, and different standard coding solutions like EVS is here, and Opus right here and right here. And we can see that Encodec performs much better compared to Opus. And if we could compute EVS for different bit rates, we could have kind of more points to compare with, but I assume computing EVS with different bitrate values is not that simple, because maybe this codec was developed only for specific range of bitrates. I don't know for this part. So basically that's it. I hope you enjoyed it. I hope it kind of shed some light on the questions on inner workings of neural encodecs. Again, why do we need this neural encodecs? Why it's so interesting? Because we can compress our audio signal into a super small, using a much smaller number of bits and transmit it super efficiently. And it's required. It's important topic. It's interesting direction actually, and there are a lot of work to be done and to be improved in this direction. Also, as some of my colleagues noticed, there is an interesting direction which is called personalized encodecs, personalized codecs. Sorry, what it means? It means we can train such models for personal like personal codecs, to compress audio coming specifically from one user. Why do we need it? We need it because we can achieve super high compression rates. Probably nobody knows for sure, but the idea is here. The idea is that with personalized codecs, we can achieve high compression rates. And if we have high compression rates and quality is also high, we have a lot of profits which we can enjoy. This is also one of the possible directions. And it wasn't explored yet in the papers. Probably it was explored within some companies, but not. It's not in the papers yet. So it's one of the direction, and I guess it's quite interesting one. Thank you for watching. I hope you enjoyed it. If you didn't like something about this video, please comment it. I will be encouraged to fix it in the future. Have a good day. Bye.